Hi, everyone. Welcome to the first lecture. In this lecture, I'd like to give a brief motivation for studying algorithms and considering things like their runtime, their correctness, and so on. So to motivate this, let's consider the problem of computing a number in the Fibonacci sequence. So I think most of you are familiar with the Fibonacci sequence. It's a sequence of numbers where each number is the sum of the previous two numbers. So you can see if we look at 2, it's the sum of 1 plus 1. If we look at 13, it's the sum of 5 plus 8. And so if I call this number f of 0, and then this is f of 1, and so on, we can define the sequence as f of n. It's the sum of the previous two, like I said, so it's f of n minus 1 plus f of n minus 2. If n is greater than or equal to 2. If n is 1, these first two numbers, the 0 and the 1, are kind of the seeds that then from then the Fibonacci sequence continues. So if you have 1, if n is equal to 1, and you have 0, if n is equal to 0. So why study the Fibonacci sequence? Well, there are some practical applications of it, but for us, it's just really a sequence of numbers. So it does appear actually in some algorithms and data structures, including the Fibonacci heap. And the pattern also appears in nature, but you can read about this elsewhere. So let me first give an implementation of this equation I've written above. And so we're going to call this Fib1. This is our first attempt at computing the nth number in the Fibonacci sequence. What we do is if n is 0, then we return 0, right? Return 0. If n is 1, we return 1. And if n is 2 or larger, then we return the sum of f of n minus 1 plus f of n minus 2. And the way I'm doing this is through a recursive call or two recursive calls to the same function. So these are here recursive calls to Fib1. Okay, this is a direct implementation of what we see here. Let's now try to understand this algorithm. And so there's three main things that we're going to ask about an algorithm when we propose one or when we're considering a problem. So the questions that we'll ask in this class, the first is the algorithm correct? Does it compute, in this case, does it actually compute the nth number in the Fibonacci sequence? The second is the runtime, also called the complexity. And the third is this more general question of, can we do better? Can we make the algorithm more efficient than the implementation we currently have or the solution we currently have? So for Fibonacci 1, this algorithm here, since it's really just a direct implementation of the definition, it is correct. I argue that it is correct by definition. For runtime, let's think about that for a little bit. So we have let's define T of n to be the number of computer steps needed to compute the nth number in the Fibonacci sequence using this algorithm. And then what do we have? Well, we have that if the input n is 0, then what do we do? So we input 0, we evaluate this first if statement, and then we return. I'm going to say that's just one computer step because we just evaluated one if statement. You might argue it's two. You evaluate an if statement and then you return. To be honest, it doesn't really matter. We're going to get the same result whether we count it as 1 or 2 or even 20. But let's just say it's 1 for purposes of this argument. So one if statement. So T of 0 is equal to 1. Following the same logic, if I want to compute f of 1, I evaluate two if statements. First, I evaluate this one, it evaluates to false, and then the one in line 3. So this is two if statements. So t of 1 is equal to 2. And then otherwise, if we have an input greater than or equal to 2, we have to evaluate two if statements. And then we do this recursive call. And in that recursive call, we have an addition. So it's going to be, it's going to be t of n. The time to compute the nth number is the time to compute the n minus 1th number, plus the time to compute the n minus 2th number, plus the two if statements, plus one addition. So this is here, this is if statements. This is the addition. And this one, we're going to come back to this because that's a bit coarse to say that it's just one computation, one computer step to add two numbers. Okay, but let me now just rewrite this so it kind of looks more like the way we wrote the Fibonacci definition. So we have that t of n is equal to t of n minus 1 plus t of n minus 2. If n is greater than or equal to 2, it's 2 if n is equal to 1, and it's 1 if n is equal to 0. And if you look at this and compare it to the actual Fibonacci definition, you see that each row, like each entry in t of n, is bigger than the corresponding entry in f of n. Right here we have f of n minus 1 plus f of n minus 2. Here we have t of n minus 1 plus t of n minus 2, plus 3, right? Because we get plus 2 plus 1. Here it was a 1 in Fibonacci, and now it's a 2, and it was a 0 here, and now it's a 1. So whatever this number is, it's actually greater than or equal to the nth Fibonacci number. So the number of computer steps to compute f of n is larger than the value of f of n. Now, how big is the value of f of n? Well, it's exponential in n. Roughly speaking, each number is double the previous number. That's not quite true, but if you look, like 34 is roughly double of 21. It's actually 21 plus 13, so it's not quite double. Similarly, 21 is roughly double of 13, a little bit less. And more precisely, we can figure this out, and it's actually 2 to the power of 0.7 times n. Right? If it was actually doubling, the nth number would be 2 to the n, so it's a little bit less. But it's still growing exponentially with n. So f of n is exponential in n, which then means this algorithm that I've proposed for you runs in a time exponential in the input number n. And that's not good. So t of n then, since t of n is at least as big as f of n, is also exponential in n. So runtime of Fibonacci 1 is exponential in n. And just to give you an example of what this means, if I want to compute the 100th number in the sequence, we're evaluating t at 100. This 2 to the 0.7 is about 1.6. So we're getting 1.6 to the power of 100, which is 2.5 times 10 to the 20. This is big enough that it will never complete, take years and years to complete on, your laptop or something like that. So what is going on here? Like, why is this algorithm so bad? It didn't maybe look so bad initially. Maybe it did to some of you, it depends, but to some, it might not be immediately obvious that was such a terrible algorithm design. And the problem was that to compute f of n, I had to make two recursive calls. One was to compute f of n minus 1. The other was to compute f of n minus 2. That call to f of n minus 1 will invoke two more recursive calls, right? Which will be to compute f of n minus 2 and f of n minus 3. And this will be to compute f of n minus 3 and f of n minus 4. And the thing that you see is we're computing the same quantity over and over again. This f of n minus 2 gets computed 2 times just in the part of the tree that I've drawn out. This f of n minus 3 gets computed both here and here, and it's going to get computed more times as we go down the tree. It'll get computed again when I call f of n minus 2, right? There'll be another one down here, actually. And as we go further down the tree, some of these numbers are going to get computed actually an exponential number of times. So we're just repeating a bunch of computation for no reason, really, in this algorithm. And so I'll just write keep computing the same quantity. So now we get to our third question, which is, can we make it more efficient? I think yes. And probably some of you, or maybe all of you, have already thought of a way to make this more efficient. And that's why this is just an example in lecture number 1 of this course. I'm just trying to give something simple to get us going. But my idea is, let's just compute each number once. Let's not compute it an exponential number of times. So how do I do that? So a faster algorithm. Well, it's not too hard. We're going to call this one fib2. It's our second attempt. It starts off the same way. If n is 0, we just return 0. Otherwise, we create an array, which has the n, a spot for each of the n plus 1 numbers going from f0 up to fn. We initialize the first two, right? The first one is a 0. The second one is a 1. And after that, we just compute, let's say, the second f2 number by summing f of 0 and f of 1. We compute f of 3 by summing f of 1 and f of 2. And so to fill in the ith number, we just sum the I minus 2th plus the I minus 1th number. And then we just return the last number in the array. This is now looking a bit better to me, right? By storing the entry in the array and then just looking it up in the array, we're ensuring we're not doing this repeated computation. So for correctness, I'm going to argue this is correct kind of by inspection, because it's really, again, just implementing the definition above. So I'll say it's correct. Let's now focus on the runtime and what happens there. So for the runtime, we have what happens. We have one if statement. We have a for loop. And inside the for loop, what do? Well, we just look up 2 entries in the array and we add them. So I'm going to say, like, the main computation that we do here is an addition. And so when this array runs from 2 to this for loop runs from 2 to n, and so we're going to do n minus 1 additions. For loop is n minus 1 additions. I'll say that's n minus 1 operations. And this first line was just using our same counting as before, 1 operation. And then what else do we have? Well, I guess I skipped line 4, right? We had to set these 2 values kind of manually in some sense. So f of 0 equals 0, f of 1 equals 1. That's 2 operations, let's say. Now, one thing you might be thinking is, some of the ways I'm counting things might be a little bit arbitrary, right? Like, why did I say this is only 1 operation? Shouldn't I have to look up an entry look up this array entry, then look up this one, and then add. Maybe that should be 3. This is also the other point I'm getting to, which we'll go into in the next lecture, which is it's kind of a fool's errand to try and actually count all of these individual computations. Instead, we should just think about like the order of the computations, like using asymptotic notation. So this is really the only time I'm going to be thinking about computing or like kind of trying to count computations. And it's just for illustration purposes. So it won't really matter because what am I getting here? Whether I call this, n-1 operations or 3 times n-1 operations, the whole point is if I sum these up, it's scaling with n instead of scaling exponentially in n. And so with my counting, I'm getting n plus 2 operations. And so the whole point is that now to compute the 100th number in the Fibonacci sequence, it's about 100 operations instead of 10 to the power of 20 operations. And this is a big difference, right? So Fibonacci 2 is efficient, Fibonacci 1 is not. That's the summary. And part of what this course is going to be about, like I said, this is just a simple example to get us going, but is to try and design efficient algorithms and try to identify inefficient algorithms and determine how we could improve our implementation of them. So let me now quickly implement these 2 algorithms just to show you how they work. And also, I'll just show you, most of you I'm sure are familiar, but we're going to be using Python 3 for the program in question that appears in each assignment. And so I'm just going to show you, a script in Python 3 where we can implement these algorithms. So I hope you see this now. This is just a sort of template. I'm importing a timing function or like a timing module so that I can just time how long each of these 2 algorithms takes. I've got fib1, which is our inefficient one, then fib2. And then down here, I'm just going to call the 2 algorithms. This is a little printer thing that's going to say, what's the value that I get for fib1 of n and how long did it take in time? And then same thing for fib2. So let's start with fib1. What do I do? Let me just move that to the side. Okay, so I have if n equals 0, I should return 0. If n equals 1, I should return 1. And otherwise, I'm going to return the recursive call, right? fib1 of n-1 plus fib1 of n-2. Okay, sorry, I wrote it in fib2. That should go up here, right? Okay, and now for Fibonacci 2 instead, it started off the same. If n is 0, I just return 0. Otherwise, I'm going to initialize this array, lowercase f. In taking a kind of Pythonic approach to this, rather than initializing the entire array, I'm just going to initialize the first 2 entries. So this is basically where I'm setting f of 0 equals 0 and f of 1 equals 1. And now I'm going to loop over, the remaining entries. So for I equals, in Python, the way I'll do this is I make a range, which is basically something I can iterate over that goes from 2 up to n. To do that, I write n plus 1 here because the way range works is it includes the first number, but it doesn't include the last number. So this will create a loop from 2 to n. And in it, I'm going to, again, do it in a kind of Python manner, which is that I append. So it's going to be beginning, I'm appending the second f of 2 to my array f, and I compute it as f of I minus 1 plus f of I minus 2, like that. Then I end my for loop and I return f of n. sorry, this should be I in range, not I equals range. That's the only thing. And now I should be able to run this. So let me run and I can show the result here. So this is computing the 20th value in the Fibonacci sequence. The first printout here is Fib1. So it computed the number 6765 and it took 0.00289 seconds. The second one computed the same number, 6765, and took 10 to the minus 5 seconds. Okay, so not a huge difference. Let's go up to 30 now. So let me run it. 30. They got the same number, which is 832040. Now Fibonacci 1 took 0.34 of a second, and Fibonacci 2 still took 10 to the minus 5. Let me increase it a bit more. I don't know, 36, let's say, and run it again. I tried this before just to sort of see what's a number that takes amount of time. And now we see we got the same number again, but to compute the 36th value with Fibonacci 1 took 6.2 seconds. And using Fibonacci 2 took, again, 2 times 10 to the minus 5. So almost instantly. So we are seeing the difference in the scaling of these two algorithms. And I mean, if I tried to compute f of 50, the first one would take forever. And the second one will, again, take about 10 to the minus 5 seconds. So let me go back to the slides. And now, one question that remains, I guess, is I said we can compute an addition takes only one step. That's not really true. And so can we really add two numbers in a single computer step? No. In general, adding two, let's say, m-bit numbers takes m computer steps. So it's typically linear in the length, not the value, but the number of bits required to represent the numbers that you're adding. If the numbers are smaller, it actually can still be not a single computer step, but it can be a constant time operation, because we have built-in hardware to do, say, 16 or 32 or even 64-bit additions. But then once you get to large enough numbers, it takes m computer steps. Now, in what we're going to do next, in the next lecture, we're going to ditch this whole idea of computing or counting computer steps. And instead, we're going to look at asymptotic notation, where instead we would say the first algorithm is big O of n, and the second algorithm is big O of something like 1.6 to the n, right? Whatever that value was. And so the first one is linear, and the second one, or actually the first one is exponential and the second one is linear. So we'll get to that in the next lecture. That's all for this one, and I will see you again soon. Okay, bye everyone.